Now that I have we have done this example, I'm going to write the formal definition of an NFA. There will be a slight difference between the formal definition of an NFA and the formal definition of a DFA. Okay, so the mathematical definition of an NFA, non-deterministic finite automaton, is a 5-tuple Q sigma delta Q0 and F. In fact, everything is the same except for delta. So Q is a finite set of states. Sigma is a finite set of symbols. Delta is what? The transition function. Q0 is the start state. F is the final state. And all definitions are the same except for the delta. Delta is the only difference between an NFA and a DFA. So for Q, sigma, Q0 and F, it's the same as the DFA. But for delta, now let's try to think of delta. Now there is a domain and a range. What's the domain and what's the range for delta in an NFA? So what's the domain? So we have to add, we have to add the epsilon somehow. So in fact, remember for the DFA was delta from Q cross sigma to Q. That's for the DFA. For a DFA, we had from Q cross sigma to Q. But here, it's not going to be sigma because we have epsilon transitions. So we will define sigma sub epsilon as sigma union the set that has epsilon in it. So we will add the epsilon symbol to the sigma, and we will define something called sigma sub epsilon. So that's going to be our domain for the NFA. Q crossed by sigma sub epsilon. And then what's going to be our range? So, before we think of it mathematically, think of it as a program. You have a program that implements a DFA. It takes a state and a symbol, and it gives you what as output? State and symbol. Let's think of it as a function, not a program, maybe a function. So it takes a state and a symbol and gives you a symbol. That's a transition. That's a transition function for a DFA. It takes a state and a symbol and gives you a symbol. It gives you a state. Sorry, it gives you a state. Now for the NFA, it takes a state and a symbol, and the symbol can possibly be an epsilon. It gives you what? Multiple states. Yeah, exactly. It can give you multiple states, so it will give you a set of states. A set of states. So that's why the range for the NFA is the power set of Q, the set of states. So P of Q is the power set of Q. What's the power set? How would you define the power set of Q? What's the power set of Q? What's the power set of a set?
It's a set of all subsets.
Yeah, exactly. It's the set of all subsets. That's what the power set is. The set of all subsets. Okay. So a transition function in NFA takes a state and a symbol that is possibly epsilon and gives you a set of states. So let's apply it to this. So let's write the transition function of this NFA in the form of a transition table. So let's write a transition table for this. So we will have a state Q0, Q1, Q2, Q3, and we will have symbols 0, 1, epsilon. Okay. Now, here we don't trace. You just put the transitions that you have in the transition diagram. You put them in the table. That's all what you do. So if you have a Q0 and you get a 0, you stay in Q0, but it's the set Q0. So it's a set of states that happen to have only Q0 in it. If you are in Q0 and you get a 1, where do you go? Yeah, Q0 or Q1. So now we're not tracing, so we're not going to say Q2 here, because we're not tracing now. We did that when we traced. We're not doing actual tracing, we're just translating what's in the diagram into a transition function in the form of a table. So we're just translating, we're not tracing. Q0 or Q1. Okay. Or Q1. Okay. If I'm a Q0 and I get an epsilon, where do I go? There is no epsilon transition out of Q0, so I go to no state, and that's the empty set of states. Okay, so it goes to an empty set of states. Yeah.
So it's not an implied epsilon transition to yourself?
And implied, no.
Because on no input, you could always stay in the same spot, right?
Okay, so again, you are tracing, you are not translating. We are translating the transitions that are in the diagram. What we are doing now is a translation, not a trace. Okay? So yes, I mean, but what does it mean? I mean, if epsilon transition to yourself, what does that mean? It means you just stay in the same state. But that's a tracing thing, not a translation. Now Q1, if I get a 0, what happens? You go to Q2. Q1 and you get a 1. Nowhere.
Yeah.
Q1 and you get an epsilon, you go to Q2. Q2 and you get a 0, nowhere. If you get a 1, you go to
Q3.
Q3. If you get an epsilon, nowhere. And Q3, if you are in Q3, if you get a 0,
Q3.
yeah, you go to Q3, and if you get a 1, you also go to Q3. And there is no epsilon transition. Okay. Questions on this? Oh, so keep in mind that the idea is an NFA takes you from one state to a set of states, all possible states that you can go to. And in general, you can have multiple states or you can have no states. So let's take another example. To see the power of in fact, for the same language, there is always a standard way. I'm going to do it again. W is that W contains 101 or 11 as a subscript. For this language, in fact, I could have drawn the DFA, the NFA. There's a standard way of constructing an NFA for a language that has an OR in it. It's the OR of two languages. We'll say more about this later. But when you have an OR, you can always say, okay, this is my start state, and then I have two possibilities because of the OR. So, and I can do it, two possibilities with epsilon transitions. Then I can draw an NFA for the language that has this as a substring, and an NFA for the language that has this as a substring, and that's all what I need. So I can say, for this as a substring, the NFA is going to be this, 1, 0, 1, and then this, and before the 1, 0, 1, I can have anything. How do I express anything?
Epsilon.
No. How do I express anything here before the 1, 0, 1? Yeah, looping on a 0 or a 1. So anything, it means anything before this string that I'm trying to match will keep you in this state. So if you get 1,000 symbols before the symbol that you're trying, the string, the substring that you're trying to match, you'll stay there. And after this, you can have anything too. And same here. 1, 1, anything. Anything. So once you get used to the NFA, it will be easy to use. So here, I'm basically specifying in the NFA, what I'm specifying is, what's the good path? Basically, I'm focusing on the good path, and I'm implicitly rejecting. It's like an implicit, without specifying anything, there is something that is not specified, I'm rejecting. So, for example, if a string does not have 1, 0, 1, it's like the string 0, 0, 1, 0. For the string 0, 1, 0, this will be rejected. How will it get rejected with this NFA? So 0, you stay here. The 1, you have two possibilities, either stay or go to this. Whether you are here or you are here, when you get a 0, it will not take you to an accept state. So for 0, 1, 0, the 0, you stay here. With the 1, you are either here or here. So you have two possibilities. But with either possibility, the 0 will not take you to an accept state. Right? So this 0 takes you to, keeps you in this state, and this 0 takes you to this. And neither one is an accept state. So when you construct an NFA, and you will get used to this when you practice more, basically you focus on what gets accepted. And you don't have to think much about what gets rejected. It will automatically get rejected if you do it right. But you will get used to it. And you'll not have to do all the tracing that we did here. So you'll be doing it in your head. So this was done only once. We did it only once so that you understand how the NFA works. But from now on, you will do that tracing in your head. Okay. Does anyone have questions? So this NFA is equivalent to the NFA that we traced. It has more states in it. That's the disadvantage. But what's the advantage? Yes?
You tracked all the possible paths with the epsilon?
No, they're equivalent. Both NFAs are equivalent. The advantage in drawing the NFA like this is that this is more systematic. So you can do this. You can use this approach to construct an NFA for any two substrings. So if I change the substrings to 1, 1, 0, 0 and 0, 1, 1, 0, you'll still be able to write an NFA this way. So you'll branch on epsilon, and then you'll do an NFA for this and an NFA for this. And that's all what you need to do. But the way we did it before, the one that we traced, was not general. The approach was not general enough to handle any pair of strings. This is general to handle the approach. I'm talking about the approach. This approach is general enough to allow you to draw DFA for any pair of strings or substrings. Okay, questions? Okay, let's do a quick one now. L is the language of strings W such that W has a 1 in the third position. Has a 1 in the third position. So that's easy. So what you do with an NFA, okay, so I have a 1 in a third position. So this is my third position. I have a 1. So what should I have in first and second positions?
Epsilon, 0.
Anything. Anything is 0 or 1. So I have, in the first position I have a 0 or a 1. And in the second I have a 0 and a 1, or a 1. And then in the third position I specifically have a 1. Then I have what?
Loop for all of them. A loop for all of them.
Yeah, for anything. So this is W has a 1 in the third position. So I specified the third position. And before it I can have anything. After it I can have anything. And I didn't have to worry about here, for example, what happens if I get a 0. I didn't have to worry about this. It's an implicit reject. If the third position is a 0, this will be an implicit reject because it's going to lead you to a dead end. If your third symbol is a 0, you'll necessarily go to this, then you'll go to this, and if your third symbol is a 0, there's an implicit reject. So the NFA basically implicitly rejects. Rejection is like implicit. You're not explicitly specifying it. And that's why it's easier to construct. Once you get used to it, it's easier to construct than a DFA. You don't have to worry about everything. Okay. Now what if I change it? W has a 1 in the third position from the end. Third position from the end. So the third position from the end. So I just need the 1 here. So let me do it in blue because I did this in blue. So all what you do is now I want the third position from the end to be a 1. And then before that I can have anything. Is this complete? Sorry, this is an accept, but I forgot to put the accept state there. So this is the accept state. So what's missing? Who can make this correct? The third position from, so this is not the third position,
No,
sorry.
it's not.
This is the last. So it's the other way around. So this is the third from the end, then 0 or 1, then 0 or 1. Sorry. So this is the third position from the end, followed by anything, anything. Now what's missing?
It needs to loop on itself at the state right before the 1.
Yeah, exactly. So in the beginning, I can have anything. So in the beginning, I can have anything. Then the third from the end is a 1, followed by anything, anything. So I'm not specifying, what the third symbol is and what the second from the end is. I'm only specifying that the third from the end is a 1. Okay, and that's why, NFAs, again, once you get used to them and once you practice, are relatively easy to use for many languages. In fact, if you try to construct the DFAs for these languages, it's gonna be hard. It's not gonna be as straightforward.